Okay, welcome to class. We left off yesterday in this discussion of Lie group and Lie algebra. To recap, a Lie group is a group that is also a smooth manifold. So this is not for every group, right? But there are certain groups, for example, the rotations, and these are groups, and this was observed and analyzed by Sophus Lie, this Norwegian mathematician, who saw that you can move in this group continuously, and this group as a space is not linear, meaning if you take two elements of the group, then, for example, the intermediate value in between will not be an element in the group. And as soon as you have structures that are non-linear, the question is, how do you parameterize these spaces? Can you find an explicit parameterization? And he realized that the way to do this is to consider for every group a tangent space to the group. And then you can parameterize this in the tangent space, right? Because the tangent space is a linear space, so you can have parameters that parameterize this linear space, and then you can introduce mappings that allow you to go from that linear space to the corresponding group element. And we saw that this can be done. Someone was asking, does it really intersect here? Not really, right? Because, so in that sense, this visualization is a little bit simplified. We saw that if you compute the derivative of R in time, so you have a family, a time parameterized family of rotations here, and then we saw that this derivative is given by W hat. Where was it? And so the derivative in time is W hat here at time 0. And the space of W hats, that forms a linear space in itself. So this space is, this space is a three-dimensional space here, the Lie algebra, and it's spanned by the 3x3 skew-symmetric matrices. They form that linear space, and that it's a linear space once you take it at the origin. But obviously here, the elements here are the identity matrix plus an offset in that direction, and that offset is an element from the skew-symmetric matrices. So we have that connection that the Lie algebra is the tangent space to the Lie group fixed at the identity element. And it's called the associated Lie algebra. And then we have mappings, the exponential map that allows us to go from a skew-symmetric matrix W hat. Once we exponentiate this, then we get a rotation matrix R. And what's nice is once we do that with this skew-symmetric matrix, so a matrix from the space little SE3, then this assures us, so it follows automatically, that R transpose R will be the identity matrix, and it also follows that the determinant of R is equal to 1. And so this is nice because it means we don't have to enforce these constraints manually or in the optimization. They are automatically guaranteed. And as I mentioned yesterday, the key benefit from a practical perspective is once you try to estimate the rotation of the matrix from images, let's say, from observation data, then you're moving, by doing this, you're moving from a constrained optimization problem where you'd have to enforce these constraints to an unconstrained one, where you just say, I take a random element from that space. It can be any skew-symmetric matrix that has these three parameters that make up the skew-symmetric matrix. And then the rotation matrix is exponentiation of this skew-symmetric matrix. And that way I have an unconstrained optimization problem that is typically much easier to work with. What we also saw is this exponentiation of matrices can be done in closed form of skew-symmetric matrix. It can be done by this so-called Rodriguez formula, and that allows me, by using sine and cosine, I can express it as something that has three terms. One is the identity, and one is an offset from the identity, that is, one is in proportional to w hat, and another term that is proportional to w hat squared. And this is not difficult to show, and it's essentially because if you take a unit length skew-symmetric matrix, v hat, then you can see if I take v hat cubed, it's the same as minus v hat. So the higher powers will just reproduce terms that are either of the form v hat squared or of the form v hat, and this is exactly what we see here. One series of terms proportional to v hat, one series of terms proportional to v hat squared. And that's nice because it means we don't have to compute this infinite power series that we have in an exponentiation. So far, so good. So this allows us to model rotations very elegantly with three. Now the question is, if in addition we have translations, how can we deal with that? And I should be honest, there are two competing ways to do it from here on. One way is that you keep them separately. You have your rotation matrix here, and then you take a translation vector t in R3, right? And that's your 6 parameters. 3 parameters here, 3 parameters there, and you're done, right? But what we can do, and we are going to do that for the sake of seeing this notion of Lie group and Lie algebra, we can observe that this group SE3, that involves rotation and translations, this is also a Lie group. So this is a group that is not a 3-dimensional group, but a 6-dimensional group. 3 degrees of freedom in the rotations, 3 degrees of freedom in the translations. With the translational degrees, you see them here very explicitly. The rotational degrees, once you phrase it with this orthogonal matrix, you don't see the 3 degrees explicitly, but they're in here, right? Because the skew-symmetric matrix, what does it look like? Well, it has zeros on the diagonal, and then it has some 3 non-zero elements here, and the negative of it on the other side, right? So this is, and so these are your 3 degrees of freedom in that you can see them in the skew-symmetric matrix. That is this, as we saw earlier, the rotation angle and the axis of rotation, they define three parameters. So this is the 6 degrees of freedom. SE3 is therefore, we saw it's a group, right? So we have neutral elements, inverse element, and one neutral element, and then inverse elements. We have a closedness. If we take 2 rigid body motions, then the outcome, the total outcome, is again a rigid body motion. And we saw that, and we also saw that we can parameterize the SE3 in homogeneous coordinates, and then each element can be written as a 4x4 matrix of this form, where we have the rotation in the top left, then the translation vector t, and then 0, 1 in the bottom. When I say 0, 1, you know, notationally, this is actually 3 zeros, obviously, right? So you have to be a little bit careful. This is not 1, 0, but since this is a 3x3 matrix, we have a row of 3 zeros here. So this is a 4x4 matrix representation of elements in SE3. And this forms a Lie group, a 6-dimensional Lie group. And what we can do is we can say, okay, if we have a Lie group, can we compute the Lie algebra that is associated with this Lie group? And spoiler alert, you won't be surprised, the Lie algebra is called little SE3, right? So we have little s, sorry, should be little SO3, but we also have little SE3, that is the Lie algebra associated with this Lie group. And what we can ask is, what is little SE3? What does it look like? And that's what we're going to do next. And one aspect is you'll see that we can, so this is an exercise, you can define all sorts of Lie groups, and you can then go ahead and try to compute the corresponding Lie algebras. What does that mean? You try to compute the tangent spaces. And we're going to do this for SE3 as well to give you this a better kind of experience with Lie group and Lie algebra, this general principle that we apply here. How do we do it? Well, what we do is quite an analogy to the thing we did with SO3. In SO3, we considered the matrix R dot R transpose. You remember we did that, we derived it. In fact, from this constraint, if you take the time derivative of this constraint, and you do the product rule here, and then you rearrange terms, you find that the term R dot R transpose is a skew-symmetric matrix. That was the observation. And R dot R transpose, what does that mean? It's the time derivative of R and times the inverse of R, right? R transpose is the inverse. So we're going to do something similar. For the group elements G that we have here, these rigid body motions with rotation and translation, we're going to consider a family of rigid body motions parameterized in time. For every time we have a rigid body motion, a 4x4 matrix that is in SE3. And then we're going to consider G dot times G inverse, which is essentially the same that we did for the rotations before, right? Because R transpose is essentially R inverse, right? If we do that, one can do the computation. I didn't do it here on the slide, but you can try it at home. You can arrange the terms, and what you get out is this kind of matrix. It's a 4x4 matrix, where on the top left you have R dot R transpose, so a skew-symmetric matrix. And on the top right you have this expression, T dot minus R dot R transpose times T. And so we take this upper right-hand element, this is a 3D vector, and we'll call it VT. Right, so this is some vector in R3. And so in other words, we showed that this G dot G inverse has the form W hat with a skew-symmetric matrix and some vector, 3D vector. And this is a little bit an overuse of notation. We will call this Xi hat. What does that mean? Xi hat, so it's overused because Xi is now a 6-dimensional vector that contains three that make up this skew-symmetric matrix and another 3 elements that make up this vector V. So it's a 6-dimensional vector and it's called a twist. We'll come to that here. And so what we see, if we take then this equation, we say G dot G inverse is, we call this Xi hat, this 4x4 matrix here of this structure. And now if we take G and multiply from the right-hand side to this equation, like we did in SO3, in the case for SO3, same structure, we get again this differential equation that says G dot equals Xi hat times G. And so that characterizes the temporal derivative of group elements over time is proportional to G, where the proportionality factor is a 4x4 matrix, Xi hat, which is traditionally in the literature called a twist. Why is it called a twist? I think, do I mention that? A twist is something that is in infinitesimal rotation and translation. So a little bit like what you do if you screw a screw into the wall, you rotate and you translate, and that's called a twist. And that's essentially what we have here. This is this infinitesimal rotation translation. And now these twists you know, at time 0 we would have the identity, so at time 0 the time derivative of g is nothing but a twist. And in other words, the twists, they form the tangent space to our Lie group, right? So now we have the same idea. We have the Lie group, some curved space, in this case a 6-dimensional space, right? So again, these visualizations that I do here, where is the visualization here? They are very abstract, right? On the paper it looks like everything is one-dimensional. Obviously it's not. So the blue space in the case of SE3 is 6-dimensional, and the tangent space is also 6-dimensional. Yes? Doesn't have to be. Yes, yes. Any motion, rigid body motion, if you look at it infinitesimally, it's a twist. That's the whole point, yeah. Yeah, so it rotates a little bit and it translates a little bit, right? So, and that infinitesimal transformation is called a twist, and this is essentially what we derived here, that showing that this space of elements of this form, top left is a skew-symmetric 3x3 matrix, top right is a 3D vector V in R3. This space is a 6-dimensional space, linear space. This space is the tangent space to the Lie group SE3. And it is called the Lie algebra, little SE3. So you can see it takes a few lines to do the derivation, and we get to this differential equation that relates the time derivative of g to the original g, and the relation is given by these twist matrices. And to clarify, you have the twist matrices, and they come out of a twist coordinate vector xi, that is a 6-dimensional vector. And what does it contain? It contains the vector v that we have top right here, and it contains w, the 3 components that make up the skew-symmetric matrix w hat. And so this hat operator, it's a little bit overused in our slides, but I didn't want to introduce new notation here. This is the operator that converts the coordinate vector to the corresponding matrix. It is the same hat that we use to convert a 3D vector to a skew-symmetric 3x3 matrix W hat, or if xi is a 6D vector, then it converts it to this 4x4 matrix. That is the twist. And similarly, like what we had before, the inverse of the hat operator we call the V operator, and this, or veg, I think it's called veg operator, and it converts the 4x4 matrix back into the corresponding parameter vector that has our 6 parameters. And so along the same lines, like with rotation, you can first take 3 coordinates W in R3, right? That was for rotations. We took 3 coordinates that make up the skew-symmetric matrix. We compute the corresponding skew-symmetric matrix W hat. We exponentiate that one. That gives us the rotation. And that way we've parameterized rotation with our W, with the 3 coordinates that make up the W. And the skew-symmetric matrix W hat. And here we can do the same. We can take a vector xi in R6. This is our 6 degrees of freedom. Then we can convert that into this twist xi hat, like we see here. And now the question is, how do we get the rigid body motion G out of it? And you won't be surprised, along the same lines, we take the differential equation and we solve it. And this is shown here. We have this differential equation. It's pretty much analogous. G dot is xi hat times G with a 4x4 matrix, xi hat now, this twist. At time 0, we assume we have no translation and identity as a rotation matrix, so no rotation either. And so this is the differential equation system that we have, and then we can solve it. By the way, in this twist coordinate vector, v and w, they have names. The v is called the linear velocity because that is the component that is the velocity in terms of translational velocity that you know from high school, right? Something moves infinitesimally, the change in translation is given by the velocity. And in the same way, the change in rotation is given by what's called the angular velocity. That's what you have when you have an ice skater spinning on the ice. They have a certain angular velocity, right? Means they rotate. They don't actually move in space, but the rotation changes, and that gives you, that is governed by this angular velocity, and that is the W. It's defined by a rotation axis and the speed of rotation. So we have this differential equation system. It has the unique solution that is given by this exponentiation. Right? Unique because we have this initial condition. With a different initial condition, you would obviously have a different solution. But if we start at identity, this is the solution we get. It's the exponentiation of this twist matrix. And here again, we can use this power series, the exponential function, the power series. So all we have to do is take an infinite sum of powers of 6 by 6 matrices. Obviously, nothing you would want to do by hand. So the question is there a closed form solution? And it turns out there is, and this is what I've shown here. Much like with the Rodriguez formula, we're not actually, well, the Rodriguez formula actually proved that it holds. Here, we're not going to do it entirely because the proof is a little bit lengthy. But you can show that if you exponentiate a 4 by 4 twist matrix, you can write it in this form, where you have the exponentiation of the skew-symmetric 3 by 3 matrix. There you use the Rodriguez formula to compute this e to the w hat. And then the top right, the 3D vector that makes the translation, this vector is given by this expression here as a function of e to the w hat and then w hat and v. So I say one can show. I'm not showing it here. The proof is a little bit longer. But it basically means that we have an exponentiation to go from the Lie algebra of these twist matrices. Once we exponentiate this, we get to our rigid body motion G in SE3. Large S, sorry, it's overlapping here. But this is the mapping, so we exponentiate and we get our rigid body motion out. That's nice. So now we can map from the Lie algebra of twist matrices to a corresponding group element, a rigid body motion. And the question is, can we also invert this again? Can we go back? Do we have a logarithm? And indeed we have. Conversely, one can show that for every rigid body motion, there exists a twist coordinate. Sorry, this is not this statement. So this shows that I can really reach every rigid body motion. For any rigid body motion, here I first showed that once you have a twist and you exponentiate, you get a rigid body motion. But you can also show that for every rigid body motion, there exists a corresponding twist. Such that, so that is actually the inverse, yes indeed. And this is called the logarithm then. So there exists a twist with 6 coordinates, making the twist coordinate vector that forms this twist matrix psi hat, such that once you exponentiate it, you get the group element. How do you prove this second statement? Well, we know that there exists a W with e to the w hat is r, so we can say this can be done. We've already seen that before. And then you merely need to show that once you have W that defines the rotation that you want, can we find a V such that this whole expression here on the top left in this closed form solution, that should make the translation vector, right? And so the question is, once I find W to make the rotation in the top left, can I find a V such that this whole expression gives me a desired translation vector T? And it turns out this can be done. One can show that one can find a vector V such that this expression holds. But again, like in SO3, this so-called logarithm is not unique. That means there are possibly infinitely many twist matrices. Once I exponentiate them, I get the same rigid body motion, the same rotation translation. And this non-uniqueness comes from the non-uniqueness in the rotation, because anytime I can rotate 360 degrees and multiples of 360 degrees around any angle, and it will not affect the rigid body motion that I get. So there exists infinitely many twists that represent the same rigid body motion. Someone was asking about quaternions yesterday. I apologize. I used to have slides on the quaternions, but for time reasons I kicked them out. I've never used quaternions myself. I should say, though, some people love them. I have colleagues in the field who work with quaternions. This is an alternative representation. I recommend, if you care about it, you can look it up on Wikipedia, how quaternions are defined and how you can model rigid body motions and rotations with quaternions. But for the sake of simplicity, I left that out of the class. So a few more words how we use these rigid body motions to represent the movement of the camera, the moving scene. So the idea is typically we have a static world and the camera moves around, but potentially we can, at some point also consider objects that move, and then you can model the movement of the camera with a family of rigid body motions, and you can model the movement of individual objects with respective rigid body motions. I say rigid objects, that would mean cars, for example, and to some extent bicycles. And humans, if you consider them as a rigid object. And in tracking, a lot of people do that. If you don't care about how the arms and the legs move precisely, but you just want to know where's the human, then possibly, let's say for self-driving applications, modeling everything as a rigid body object is okay. You might not care too much about how the leg moves, right? You just want to know where is the person at any given moment. And so this approximation actually works fairly well for a lot of objects. Depends on the application. And for all of these, you would use a rigid body motion if it's applicable, and then you can use these Lie algebra representations to model it. So here the idea is now, and this is introducing a bit of notation, we have a world, a point in world coordinates. So this is some point in the world, in some world, fixed world coordinate system. And then I observe that point from a camera that moves. And typically, once I have a moving camera, I would have a camera coordinate system. So that is the world relative to my camera, where I have an origin, let's say, in the center of the camera, and a z-axis that points in viewing direction, etc. And so I have a coordinate system that moves around with the camera, and then I can ask, what are the coordinates of a point x0 once I observe it from a different camera vantage point with a different coordinate system? And the difference in coordinates is just given by a rigid body motion, right? And that is a rotation and a translation. There is sometimes confusion as to whether xt is r x0 times t, or whether it's vice versa. that depends on how you define things, right? You can also say x0 is r times x plus t, and then you have the inverse transformation in a way. So you have to be a little bit careful what convention you stick to, but here the idea is that you have a relative rigid body motion between the static world coordinate system and your camera system. And that is governed by some rotation and translation, and so you can, for example, phrase it in this way. You can either write it in 3D coordinates, rx plus t, or if you like, you can write it in these homogeneous 4D coordinates that we've seen, and then you would just write g times x0. And now you have to be really careful. The x0 in the box is a 3D vector. The x0 in the equation at the bottom is a 4D vector. So strictly speaking, is not the same thing. And strictly speaking, you should use different notation. But you can imagine if I take a 3D vector, x0, in R3, and then I add, make it in homogeneous coordinates, which basically means I take the vector x0 and I add a 1 to it. I could call this, if you really insist, I could call this x0 bar or something. But once I do that, everything gets more and more complicated, right? And so for simplicity, I'm just overusing the notation here. All the x's can be either in 4D or in 3D. Now you might wonder, well, how do I know which one I'm looking at? It's very easy. If you have a little g here, this is a rigid body motion is a 4x4 matrix, then whatever it multiplies must be a 4D vector, otherwise it doesn't make sense, right? So it's actually not difficult to see whether the x0 that you're looking at is a 3D vector, like up here, or a 4D vector. If it's multiplied by a rotation matrix, it must be a 3D vector, because rotations are 3D rotations. If it's multiplied by a little g in a 4x4 matrix, then it should be a 4D vector, right? And then it basically means this is in homogeneous coordinates. So, this is, you have to read the notation properly and distinguish, but I apologize, I just didn't want to overload with too many bars and zeros, otherwise you can get lost in too much notation as well. And typically you would stick with either this or that representation to work with. And again, the benefit, you can see it here, why would you go into 4D homogeneous coordinates? Things get simpler. You just have matrix vector multiplication and terms get shorter. And if you do multiple transformations, you concatenate them, then you just multiply the g's, right? Whereas if you have rotation translations, things get very lengthy. That's why this gives you often much more compact ways to compute things, to write things down. Here you see it, right? Once you consider, for example, different observers, let's say you have one camera here and a different camera there, then you can say the point, so given two different times, right? So it doesn't have to be two cameras, but the same camera times 0, times 1, times 3, right? Then the same point will have different coordinates. And if I want to know what are the coordinates of a point in camera 2 that had certain coordinates in the camera 1, let's say the point's coordinates in camera 1 are x of t1, and I want to know at time t2 what are the coordinates if the camera moved, then it did a motion between time 1 and time 2. I call it g t2 t1 is the camera motion between frame 1 and frame 2, and then they differ by this rigid body motion. Right? And if I define things this way and say the rigid body motion that relates the coordinates at time 1 and time 2 is this g2 t1, then I can do things like saying, how about if I look at it at time t3? Compared to the coordinates at time t2, it is just g of t3 t2 times x of t2. And x of t2 as a function of the coordinates at time t1 is exactly g t2 t1 times x of t1, right? But then I can also say this in the image 3, there is a rigid body motion between the first and the third camera, that is g t3 t1 times x of t1. And this should hold for any points, right? Any point that I consider, I should have this relationship with a rigid body motion moving from time 1 to time 2 or time 1 to time 3. And that means this family of rigid body motions has to fulfill for any t1, t2, t3, it has to fulfill this property. You can see it here, right? Because, where is it? Clearly, for this to hold, I need to, for any point x in the coordinates of the first image, I need to make sure that basically this expression here must be the same as this expression here. And so that way you can transfer coordinates from one frame to the other. And here, believe me, it's really nice if we do this transformation with a simple matrix multiplication. Because then doing multiple consecutive transformations just means you multiply the matrices. If you were to do this in this representation that most people tend to use, rotation plus translation, you get a mess. Every time you add a new transformation, you have to multiply with the matrix and add the translation, and then you get more and more terms in your expression. It doesn't look pretty, whereas here it's still fairly simple to concatenate. That's one of the reasons why you like this homogeneous coordinates, because expressions stay fairly simple. Transformations are just matrix multiplications. And along the same vein, you can transfer coordinates back. So you can say, what is the coordinates in frame 1 relative to the coordinates in frame 2? This is gt1, t2, the transformation from t2 to t1. And then x of t2, we saw, is the same as gt2, t1 times x of t1. And since this should hold for any point x in the coordinates of the first image, we can read off that gt1, oh, sorry, that was not clever. gt1, t2, sorry, where is it? This thing here must be the identity, right? So we can read off gt1, t2 times gt2, t1 should be identity. This is almost trivial, right? The transformation from frame 1 to frame 2 should be the inverse from the transformation from frame 2 to frame 1, obviously, right? So gt1, t2, t1 inverse is gt1, t2. There we have it. All right, and so this way you can see, you can use these. Why am I showing you this? This is not really profound. It's just to show you how you can use rigid body motions, 4x4 matrices, to transform between coordinates in different systems. Maybe one thing that you can consider is how is velocity transformed. So let's say I have objects that move and I observe their velocity in one frame, and then I have a different frame that is different from the first one. How is that transformed? So let's say we have a point x0 in frame t, and the coordinates over time of that world coordinate point are given by xt is gt times x0. And then I can see how do these coordinates, so this is now the camera moves, the point doesn't actually move, but the camera moves, right? And then I can ask, what is the observed velocity in the coordinates, right? Because once the camera moves, at least what I see is that the coordinates of a static world point observed from a moving camera, they change over time, like so. And then that gives rise to this velocity. X dot is g dot times x0. And then we saw that g dot for these Lie group elements can be written, then we go back, into the coordinates of the point in the current camera, and that is g inverse times x. And so we see that we have this equation, x dot is g dot g inverse times x. And g dot g inverse, we saw this is an element from the Lie Lie algebra. And this is notoriously so. As soon as you consider derivatives, time derivatives in Lie group structures, you can expect the Lie algebra will pop up, because that's the tangent space. That's what you can expect. And so you can see that the velocity of that point, as observed in camera frame T, is given by a Lie algebra element times the coordinate vector. And this we call the twist matrix, G dot G inverse. We saw this is these 4x4 matrices from little SE3. And so we can write the velocity is a twist matrix times the coordinate vector. You can also go to 3D, and I sometimes do that. So often we work in homogeneous coordinates, but you can always map things back to 3D coordinates, right? And then you plug in this twist matrix, and then obviously you can write it as W hat times X plus V. And so this symbol V hat, these twist matrices, these 4x4 twist matrices from the Lie algebra, they represent the relative velocity of the world frame as viewed from the camera frame. And maybe one last thing, because it does pop up in the literature every now and then, is this notion called the adjoint map. And I wanted to mention that so that you have at least heard of it before. I don't think we're going to use it much, but it's not bad to have heard of what that refers to. Suppose you have a viewer in another frame A. So that a viewer in another frame A is displaced relative to the current frame by some rigid body motion gxy. So we have a frame in it that we call y. And there is a rigid body motion relative to the camera. So we have one camera here that moves over time and observes the world, but then we have a different one that differs from X by this rigid body motion. Then the velocity that is observed in the new frame differs from the one in the old frame by this rigid body motion. And then X dot we saw as V hat times X. And if we express that x back in the coordinates of y, then it's g inverse, gxy inverse times y. And so what you see is, if x dot is given by v hat times x, then y dot is given by g v hat g inverse times y. So in other words, the relative velocity of points observed from camera frame A is if in the original frame X, the velocity is given by v hat, by this twist matrix. In the new frame A, it is given by g v hat g inverse. And this is this transformation where you multiply the twist matrix from left and right with g and g inverse. This is called the adjoint map. So it's a map where you take a twist matrix from the Lie algebra and transform it to a different twist matrix by multiplying with the group G and G inverse from either side. And so this is called an adjoint map. It pops up in some calculations if you consider, different coordinate systems, and you want to know what is the observed velocity for this observer relative to the velocity that the other observer observes. Then you often end up with these adjoint maps popping out. Nothing really profound, but you can see how this comes about, how the adjoint map comes about. And this is a mapping on the Lie algebra that allows you to move from one element to the Lie algebra to another one. So to summarize this aspect, that the aspects that we discussed, this whole idea of Lie group and Lie algebra, we considered two different Lie groups. One was the rotations, SO3, and one was the larger Lie group, the six-dimensional Lie group, SE3, where you, in addition to the rotation, you have the translation as well. And you can represent them with matrices. In the case of rotations, you have a 3x3 matrix that is invertible, that is orthogonal and has determinant +1. In the case of rigid body motions, you can write it as a 4x4 matrix in this form if you want. But you can also use 3D coordinates, right, to write it. So instead of having the homogeneous coordinates, you can write it as rotation plus translation of some vector x to get a new vector. And since these are groups, you always have inverses, right? In the case of rotations, the inverse is this matrix is the transpose. In the case of rigid body motions, you have this inverse. Did I show that? I'm not sure, but you can do it for yourself. If you multiply this G with this G inverse, you get the unit matrix. It's not difficult to do, but always useful to do it at home to get some hands-on experience. We saw exponential representations that we would use in practice to have an unconstrained optimization problem. In the case of rotations, we get these twist matrices, we exponentiate. In the case of rigid body motions, we expand the twist matrices by this linear velocity vector, and once we exponentiate, we get the 4x4 rigid body motion. And we discussed velocity transformations, and we discussed the adjoint map. Let me see, do I have time for the Euler angles? I think I have to. I saw the follow-up lecturer is already waiting. Let's close it here, and I'll do the Euler angles next week. Thank you.